All right, folks, we are going to go over Chapter 18, Slide 8. Before doing so, I think it's going to be useful to review Slides 6 and 7 from this chapter. In Slides 6 and 7, we were looking at a couple of different titrations. We were looking at the titration of a strong acid with a strong base and of a weak acid with a strong base. And there are different approaches for looking at these. And basically what you want to see, there's an experiment you do where you have your acid in a beaker. Let's say 0.1 molar HCl, so it'd be a strong acid. And you're going to drip some sodium hydroxide solution into this. And you monitor the pH. So we would have done this with microlab. And what happens is you get a graph of pH versus volume of base added. And you get sort of a plot that looks like this. You have an initial pH, you start adding the base and the pH goes up, kind of flattens out a little bit, and then when you get ready to hit that equivalence point, it just shoots up like a rocket, and then past the equivalence point, it flattens out again. And the midpoint of this rise, actually, if you've had calculus, it's where the curve goes from concave up to concave down. The midpoint of this rise is the equivalence point. And so these past few slides, we've been basically trying to get an idea of what happens at various regions in this titration curve. So it's important for us to understand the chemistry that goes on in each of these two cases. Let me talk about that a little bit. Let's look at these two different cases. So here on this side, we'll look at the strong acid, and on this side we'll look at the weak acid. And in both cases we'll be adding strong base. So I'm going to just draw my beaker here with some H plus in it, and I'm just putting H plus for the strong acid because it's dissociated. All this stuff, whatever it is, it could be chloride, it could be nitrate. We don't worry about the counter ion when we're dealing with the strong acid. On this side, however, we have a weak acid, and we envision it in the titration problems as pretty much being undissociated. Of course, there's a little bit of this that has dissociated, but you're not going to worry about that. All right. In this case, the reaction that'll occur is you'll have protons plus hydroxide going to water. In this case, after you add the base, you form something that does not affect the pH. In this case over here, you have the weak acid that reacts with hydroxide, and that forms water, and the counter ion, or the conjugate base to the acid, to the weak acid. In this case, you are forming something that affects the pH. And as a result of that, you look at these two things a little differently. This case is a bit easier. In this case, all you do is you basically keep track of either the H plus concentration or the hydroxide concentration, and you're good. You can find the pH from that. For example, if I was going to find the pH of this solution, we'll say this corresponds, just to make it easier on ourselves, this is going to correspond to a 0.6 molar solution. Well, then the pH of this would be the negative log of 0.6 molar. Now, after I add the first hydroxide and make water, well, now we got a 0.5 molar solution. So we take the negative log of 0.5 molar. We add another hydroxide, and now we'd have the negative log of 0.4 molar. I think you see the case, all right? You can add another hydroxide, 0.3 molar, another hydroxide, 0.2 molar, another hydroxide, 0.1 molar, aha, but at this point, at the equivalence point, now you're basically at pH 7. If you got a neutral solution, all the carbon dioxide's out. Past equivalence, now we take the negative log of 0.1 molar hydroxide as our POH, and we'd find the pH from the POH. So this case is pretty simple. This one's a little tougher. At the beginning of this case, let me just move this up a little bit. At the beginning of this case, it's going to be just like a regular old weak acid problem, where we'd say, okay, you have a 0.6 molar solution of a weak acid, and that's going to dissociate into H plus and A minus. And I'm just going to call this the molarity of the solution, whatever that happens to be. You're going to lose X amount. You're going to gain X amount of these. So you can get the molarity minus X, X and X. And we'd end up setting this up as X squared over the molarity of the acid minus X is Ka. In almost all cases, this will be 5% or less of this. And so we get X squared over the molarity of the weak acid is Ka. We multiply both sides by the molarity, and we end up getting X squared is Ka times the molarity of the acid. We take the square root of both sides, and we find that X, which is the H plus concentration, is the square root of Ka times the molarity. Since we want the pH, this is at the start before we've added any hydroxide, we want the negative log of H plus, right? So we just take the negative log of the square root of Ka times the molarity for the initial pH. Pretty simple. All right, now the problem is what happens when we start to add hydroxide to this system? Well, let's see. If I add a hydroxide to this system, I'm going to form water, and look what happened. I've got some conjugate base that's present. So as soon as I start adding hydroxide, this system's going to end up changing a little bit. Now we've got a buffer. And so once I've started adding hydroxide, I'm going to use the buffer equation. pH is the pKa of the acid, whatever that happens to be, plus the log of the amount of base over the amount of acid. It would be the concentration of the base over the concentration of the acid. In this particular case, we're going to take 1 over 5. Let's say I add another hydroxide. Well, let's see, we're going to make water and an anion, the conjugate base. So in this case, it'd be pH is pKa plus the log of 2 over 4. Notice both of them change, right? Because when hydroxide reacts with our acid, we lose the acid and gain the conjugate base. So at this point, notice I've added 3 of the hydroxides of the 6 necessary, and this is a special point here. I'm at the half equivalence point. I'm halfway to the point where I've added enough hydroxide to completely react with all the acid. We call this the half equivalence point. It's a special place because at this place we see that we have the pH is the pKa plus the log of 3 conjugate bases over 3 conjugate acids. The log of 1 is 0. So at the half equivalence point, the pH is the pKa. So in such a titration curve, such as this one, if we're actually doing a titration of a weak acid with a strong base, and this is our equivalence point, we'll say 100 mils, we can go here to 50 mils, which is the half equivalence point. We can find the pH that corresponds to the half equivalence point, and that's the pKa for the acid. That's pretty cool. So if this was an acid with a pKa of 5.1, then the pH at the half equivalence point, we'd expect it to be 5.1. All right, let's go back to our titration. Let's continue to add hydroxide. Add hydroxide here. We get a water and an anion. So the pH at this point, I shouldn't draw it over there. That might get confusing. The pH at this particular point is going to be the pKa plus the log. Now there's more conjugate base than acid. I add another one, make it my water and my anion. In this case, the pH is going to be the pKa plus the log of 5 over 1. And if I add one more hydroxide, I've got all conjugate base. So you might say, let's use our buffer equation and say pKa is pH plus the log of 6 over 0. Well, there's a big problem there. I hope you recognize what the big problem is. You don't want to divide by 0. So we can't use this equation anymore. Once you've reached the equivalence point, notice we're at the equivalence point. We've added the equivalent amount of hydroxide necessary to react with all of the conjugate acid. So really at this point, we've now turned it into a question of what is the pH of this solution that contains only the conjugate base. That's going to be a little different. So what we would need is we need the molarity of the base. You're going to have to figure that out. It's not too difficult. I went over that in the last time. And, well, we'd say, the anion would react with water, and it's going to form the conjugate acid and hydroxide. And this happens because this base accepts a proton from water to form this, and of course the water then turns into hydroxide. The initial concentration of this is going to be the molarity of the base at the equivalence point. There's going to be some change that occurs to get us to equilibrium. We don't have to worry about water. We're going to assume none of this is present. We're going to lose a little bit of the conjugate base. It's going to gain X amount of the acid and hydroxide. So we're going to get the molarity of the base minus X at equilibrium, X amount of this and X amount of that. So we'll be able to set up an equation, X squared, of the molarity of the base minus X. What's that going to be equal to? It's going to be equal to Kb for this conjugate base. Usually, this is going to be 5% or less of the molarity of the base, simplifying the math. I'll multiply both sides of this equation by the molarity of the base, and I end up getting X squared is Kb for the conjugate base times the molarity of the base, whatever that happens to be at the equivalence point. Which, remember, the equivalence point on the titration is right here. It's right there. All right, taking the square root of both sides of this, I would get X is equal to the square root of Kb for the base times the molarity of the base, and then the POH is going to be the minus log, this is X, of the square root of Kb for the conjugate base times the molarity of the base. And of course you can get the pH from the POH. Remember, pH plus POH is 14. We have looked at this region of the curve. We've looked at this region of the curve. And now we've just looked at equivalence. Now we have to look at the case where we're past equivalence and we continue to add hydroxide. So in this case, we're past equivalence, and if I add more hydroxide, that hydroxide survives. There's nothing there to react with it, and it just starts building up. So past equivalence, once you're in this portion of the curve, you just have to keep track of the excess hydroxide concentration. So, you just figure out how much is there. And in this case, your POH is basically just going to be equal to the negative log of the excess hydroxide added. So now we're ready to look at PowerPoint for Chapter 18, Slide 8. In this case, we're going to look at a sort of diagram of the titration of 8 molecules of a weak acid, HA, with hydroxide. So this reaction is going to take place. The weak acid is going to react with hydroxide to form water and the conjugate base. And remember, this affects the pH. Down here, we have a solution of the weak acid. Up here, we have some hydroxide ions that we're going to drip into the solution through a titration. this is the pH at the start. Over here, this is the equation we're going to use for it. I showed you this before. The pH at the start will be about equal to the minus log of the square root of the molarity of this weak acid times Ka for the acid. Now we're going to start adding in some hydroxide. Here we go. In it goes, and it reacts. And notice what happens. When the hydroxide reacts with the weak acid, it forms the conjugate base. So at this point, we're going to use this equation over here. pH is pKa. Wonder why I'm taking the log of 1/7. Well, let's count. 1, 2, 3, 4, 5, 6, 7 weak acids, and 1 of the conjugate base. So the 1's up here and the 7's down here. So the pH is going to be the pKa, which in this case is 5, plus the log of 1/7. And notice on this graph here, on this axis is pH, and on this axis would be the milliliters of 0.1 molar sodium hydroxide added. This represents the titration of 100 mils of 0.1 molar of a weak acid with a pKa of 5 with 0.1 molar sodium hydroxide. Now you should notice that the equivalence point is 100. When we add 100 mils of the 0.1 molar sodium hydroxide, we'll have completely reacted away all the weak acid. So at this point, we're only 1/8, I should say. We're only 1/8 of the way to equivalent. So I've only added about 12.5 mils at this point, and the pH is around 4. Now I'm going to add in another hydroxide. So this would be the case where I've added 25 milliliters. Boom, we get a reaction. And now in this case, at 25 mils added, I'm 1/4 of the way to equivalence. But at this point, I have 2 conjugate bases relative to 1, 2, 3, 4, 5, 6 of the weak acids present. So my pH here is going to be my pKa plus the log of 2/6. And I'm at 25 mils added. Now let's add another hydroxide. This would correspond to 37.5 mils. And at this point, you can see 3 conjugate bases and 5 conjugate acids. Now this next step is a special spot, 50 mils added. We're at half equivalence, folks. I've neutralized half of the acid, which means half of what's present is the conjugate base. At this point, it's a 1-to-1 ratio. I have equal amounts of conjugate acid and conjugate base, so I have the log of 1 over here, and the pH is the pKa at the half equivalence point. So here I'm at 50 mils of the base added. I go up here and look over, look at that. The pH is 5, which is the pKa for my acid. That's kind of cool. Now we're going to continue to add. Here I've added 62.5 mils of the base. The pH continues to go up. I'll add another one. Now I'm at 3/4 of the way to equivalence. In this case, I've added 75 mils. And notice, I have 6 conjugate base, a ratio of 6 conjugate base to 2 conjugate acid. The next step, I'm 7/8 of the way there, so I've added 87.5 mils of the strong base. My pH will be pKa plus the log of 7/1. You'll have to do reaction stoichiometry to figure out what these numbers are. Now here's a very special point. Notice what happens when I add the last hydroxide to consume the last weak acid. Boom, that pH shoots up like crazy. I can no longer use the buffer equation because I don't have a buffer here. There's none of the conjugate acid present. I've used it all up. So at this point, this becomes a weak base problem, very similar to the weak acid problem that we had at the start. And in this case, we'll find the POH, and that'll be about equal to the minus log of the square root of the molarity of the base, whatever that happens to be at this point, times Kb for the weak base. Now, past equivalence, this hydroxide's going in, and there's nothing there to react with it. It survives. So I have a hydroxide here that's excess, and that's going to drive the pH. So what I'd do is I'd find the POH first and take the negative log of whatever the concentration of this hydroxide ion is, and once I find the POH, I can find the pH.